This is Nicco, I'm Sam, and we're going to be talking about the Verkiestercone problem. Alright, so let's have a race. We have here car A, car B, and car C. So the objective of this race is to get from the top point there to the bottom point in the shortest amount of time. Now we provided you with three options. We have for car A line, which is, as you know, the shortest path. We have for C a steep exponential curve, which would take the most advantage of gravity's acceleration. And then we have B, which is something sort of in between the two. So this is a variation of something called the Verkiestercone problem, which is at its core such. If you are in a vertical plane where the only forces that apply are gravity and the paths that a disk can roll on, what would be the path of least time that a disk can roll on from point A to point B, such that point B is below, but not directly below point A, because obviously that would just be a straight line. This problem has actually perplexed famous scientists and mathematicians for years before us.
So this problem has been around for almost hundreds of years, and because of that, we have awesome scientists and physicists that have tried to take on this problem. And so if you look at the names, we have Isaac Newton, Galileo Galilei, and Johann Bernoulli. And there's a little bit of a time difference. As we know, Galileo had a lot before Isaac Newton and Johann Bernoulli, but that is important. So Galileo's theory, although it was incorrect in the end, was a great precursor to especially Isaac Newton's theory. Galileo thought that the fastest way between 2 points is an arc of a circle. Now he was right in that the fastest way has to do with circles, however his actual theory was incorrect. And eventually, Johann Bernoulli found out that he was incorrect. And since Johann Bernoulli wanted to find the fastest way, he created a little competition. He sent out an invitation to all the best physicists and mathematicians in Europe, and he held the competition to see who could find the fastest way. And Isaac Newton, upon hearing this news, was a little bit irritated. He was a little bit infuriated that a lesser scientist, such as Johann Bernoulli, was challenging such a masterful mind as Isaac Newton. And because of pride, he did it in one night. He completed the problem in one night. Johann Bernoulli took around 2 weeks, however, they both figured it out. And in fact, they used completely different methods.
Alright, so Bernoulli used a property that some of you may remember from physics class called Snells Law. So to understand what it is, we're going to show you the beach problem. So the problem starts, you and your friend are playing catch with a ball at the beach. You're standing in the water and your friend's standing on land. So as you throw the ball, you realize that because you've been spending all night in your room studying Snell's Law, you haven't actually had the chance to make any friends. So you're standing there in the water and the ball is on the shore, and as the Snell's Law enthusiast you are, you want to get to the ball as fast as possible. Now, the thing is, the water is much more viscous, obviously, than air, and you travel much more slowly in water than on land. So the shortest path, the straight line, will not end up being the fastest because the water will slow you down and reduce the time significantly. So maybe you'd think that you'd want to make a cut straight to the land with a perpendicular line. And it turns out that, this is going to get complicated for a second, that the angle, when the ratio between the sine of theta 1, as you see here, is of theta 1 and the sine of theta 2 as the angle created here equals the velocity that you're able to travel in water over the velocity that you're able to travel on land. You will have the path of optimal time. And, unsurprisingly, this law also applies to the fastest known thing in the universe, which would be light. So, using this, Bernoulli was able to take little segments of different materials, and as he shone them through, they all refracted according to Snell's law, and thus created the Vertier-de curve.
So as I stated earlier, Bernoulli and Newton came to the same conclusion with completely different methods. And Newton's method used a cycloid curve to find out the fastest way. He actually used calculus to prove the cycloid curve. And before I can get into what a cycloid exactly is, I need to explain what a roulette is. Now, the roulette is the path that was created by a point on a rolling polygon. So this is very important, so I'm going to repeat it. It's the path that is created by a point on a rolling polygon. Now, that may sound redundant, but when we get into something like a trochoid, that's a very specific roulette. It's the same exact thing as a roulette, except it has to deal with, instead of polygons, a circle. Now, we can get even more specific. We can get to finally the cycloid. Now, a cycloid is, put simply, everything I just said, just the point is on the circumference of the circle. Now, that's what Newton used to find this, to find the Vertier-de, and that's how we actually figured it out.
Okay.
And we use something called the spirograph to make sure that our Vertier-de curve was extremely accurate and precise.
You can. Oops.
So that would be an example of a roulette, a cycloid, and a trochoid.
Okay, so we thought that you might like to see the application of this in real life.
So we made a model using what we've learned with cycloids and spirographs. And we have, it's very similar to the race, we have our straight line, our exponential curve, and a mysterious other one. It's the cycloid.
If you rotate it more this way, then I think everyone can see it.
Alrighty.
Is everyone good?
Yeah. Thank you.
All right, people in the front row, watch out. All right, ready? 3, 2, 1.
Now that was extremely fast. For you guys, we have a pre-recorded video. It's super slow.
Nice.
And now it's
all right, so as you can see, the cycloid reached the bottom first, and just so everyone knows, that is not a coincidence. We have tried this many times, always the same outcome. So you may be wondering, how do you find this without Snell's law or a spirograph?
So, this is a little bit difficult. This is how. Sam and I, we're only freshmen. We have not tackled calculus. Calculus is a little too hard and distant. So, yeah.
That's why we would stick to this. All right, so our final property that we would like to talk to you about that has to do with cycloids is not that it reaches the bottom before any
One.
Oh, nice.
Cool. So again, that was pretty fast, but lucky for you, we have a beautiful pre-recorded video.
And I don't, if you noticed, you would see that right here, right at about this point, the ball behind hit the ball in front. And the reason why is because they're both tangible objects. And they can't pass through one another, although in theory, if you had some sort of ball or other rolling object, it would actually pass directly into the one in front of it, and they would both reach the bottom at the exact same time, perfectly lined up with each other.
Another tangible thing is that there's friction in this model, and in our perfect world, there would be no friction.
And the final message we'd like to leave you with is that it's very important to remember that at the Todachrome, we call Marin Academy. Everyone's a winner.